Beware the Jabberwock gamers. My name is Matt, and I make games and other things. In Game Design Game, I share my game design processes and ideas so that you can follow along a little bit in the creative process. In recent years, I'm sure some of you have noticed the rise of artificial intelligence and generative AIs for processing language and images and many other things. AI is only going to keep growing into new areas and approaches. As I started to notice the new developments in AI, it reminded me of some work I did a long time ago in the early days of neural networks using self-organizing feature maps for natural language processing, sort of. This was 30 years ago, and so by modern standards, very primitive stuff. The core concept of this project was to try and teach a neural network to learn the rules of spelling in English such that it could recognize a poem like Jabberwocky by Lewis Carroll with many made-up words as valid words, and at the same time still call out misspellings and errors as errors. So this was essentially to introduce it to rules so that it could then apply those rules to new and unfamiliar words, and to see what was involved in that. In episode 9, not a game, but an interesting topic anyway. Game design game. So I have a degree in computer science, and back in my college days, I did research in what was then a fairly new field of neural networks. But I also had an interest in linguistics, the science of language. And so I decided to combine those two for my research project. The idea was to make a neural network that could learn the rules of English spelling by example, such that when shown brand new words, it could fairly quickly recognize them as correctly spelled, even if it hadn't ever seen them before. While at the same time, words with actual errors, such that they would not be viable English spelling, that it could recognize those as errors as well. So the particular type of neural network I was working was called a Cohonan feature map at the time. Self-organizing feature map is a more general term. And the idea is it's a neural network that learns by example using the inputs it's given as the training values. It's never told whether the input is correct or incorrect. It is instead works under the assumption that it will receive much more correct information than incorrect information. And so the correct data moves it in the right direction. The incorrect data moves it in the wrong direction, but it's so infrequent that it doesn't spoil the overall results. Applying neural networks to spelling posed some tricky challenges, which I'll get into later. So I had this idea of training the neural network, but the question then became, okay, how do I give it a proper test? And the idea I had was to train it on the poem called Jabberwocky by Lewis Carroll. This poem is filled with made-up words, but they are spelled in ways that are consistent with English spelling, and through context, a reader can grasp the meaning. So I had no intention that I was going to teach this neural net what the words meant, but I did want it to at least get to the point where it could be shown the poem Jabberwocky and conclude that all of those new words were at least viable English spelling, even if it had never seen them before. Before I get into the details of my specific project back then, I thought it'd be fun to show you a little bit about how these feature maps work in general. So I'm going to switch to a view of a little demonstration program I made using Unreal Engine. So this is a crude demonstration of self-organizing feature maps. As you can see, I've got 3 demonstrations set up here. I'm going to run them all at the same time. Back when I originally did this sort of thing, it was very slow. The computers were very slow. So these things would run overnight. However, everything's fast enough now that I can run this in real time and you can see what's going on. So the idea of a self-organizing feature map is that it consists of a lattice of nodes. So each of the intersections on these shapes is one node of the network. The nodes are linked to neighbors. So each of the lines you could see drawn, intersection, intersection, is a linkage. The linkage does not take up any memory. It doesn't have any numbers associated with it. It is simply a way to associate each node with a handful of nodes that are considered to be nearby. And each node, however, has as a value. In this case, the values are going to be 3D points in space. And the idea of the self-organizing feature map is that I will be giving each of these nodes points in space as their input. And these maps are going to be attempting to learn the shape that creates the points that I'm giving them. And the way that it does that is it finds the node that is closest to the sample point, and it moves that node closer to the sample point. And then it also moves some of its neighbors closer to the sample point. And so each sample point it gets tugs these graphs out of shape, out of this starting shape that I've got, and closer to the shape of the points that I give it. As you can see, some of these networks have different numbers of nodes. So the purple one on the right is made up of a very small graph, a total of 49 nodes, 7 by 7, and is only connected each node to at most 4 neighbors. The graph on the left, the blue graph, as you can see, has quite a few more nodes, 225 nodes in fact, and each node is connected to up to 6 of its nearest neighbors. And these will behave slightly differently. I will also be giving each one different test shapes. So when I start these nodes running, you will notice they start to crinkle up. They'll initially look very strange and like wrinkled pieces of paper. But after a short while, you will be able to visually identify the shapes that are being fed to each of these nodes. I don't think I'll have to tell you what the shapes are. I'm hoping these nets will get close enough to show you. And what that really means is that the neural net has become the shape that I'm feeding it, and could give me feedback if I give it new points. Eventually it would be able to tell me with decent accuracy whether the point is on its shape or not. There are some caveats to this, and I'll explain them after you see, because I'm sure nothing is going to go perfect here. I'm not going to run these for a long time. Normally they'd run for millions of iterations. I'm going to run them for several thousand. So let's just take a look at what these self-organizing feature maps might do. So the numbers at the top are just helping me recognize what goes on here. The iterations is how many points I've given them to process. The alpha is how strongly each input tugs one of those nodes. You can see the center one got some bad data that's pulled that white node very far out of position, but then the correct data now is pulling it back into position. The radius text for each of these nodes is telling me for each point it's fed, how far away does it tug its neighbors. So it started at a radius 3, so each node would pull nodes up to 3 jumps away, but now it's down to a radius of 1. So each correction only tugs the nearest neighbors. I'm sure, although there's plenty more this could do, you can already tell roughly what these shapes are. There's definitely imperfections in this process, but I'm just sort of giving you the idea of what they might be able to do. So you can see this one on the right, the magenta purple colored shape. It's trying to feed a square, but the node is so small that it's really struggling to cover that front face in this case. The central one, very easy to identify as a cone. And like the other one, you can see that there are gaps that it was unable to cover. And this is one of the flaws of this approach. And then the one on the left here, you can see that that's trying to be a sphere. There's definitely some missing bits here, including, it's a little hard to tell, but there's a bit of a twist where the sphere got folded over itself. And yet otherwise it's fairly stable and at least identifiable to our eyes as being a sphere. So to really demonstrate these, and make them work better, I would need to spend a lot of time playing with the rate at which these change, the number of nodes perhaps, maybe how far off my error points are during training. There's many ways that I could improve this, but those take a lot of time to hone in on. So this is really more just to give you an idea of how these self-organizing maps work, so that when I talk about the project I did for my thesis, you'll have a better idea of what these terms mean when I say it's going to converge toward a solution. So you've seen how self-organizing feature maps might be able to take in spatial data and approximate that shape in its network. And what that would allow someone to do, again, is to test input data, make conclusions about whether it's part of that shape or not, and possibly even correct bad inputs once it stops reacting to them so heavily. The training settles down after time, specifically so that those errors do not pull things out of shape nearly as much after it's had a chance to train sufficiently. So the project that I did was to try and take this principle and apply it to spelling. And so the idea would be a self-organizing map. It is given words as inputs, and essentially the goal is that it corrects the spelling of the word and provides that word as output. So by correcting the spelling, I mean, if I give it a word where I've introduced an error that takes it away from proper spelling, that the feature map can recognize that it is an error, and by picking that sort of closest match node concept, can substitute in a better suggestion. So how do words map into these nets? Well, that was the biggest challenge of this project, and probably also the thing that I never quite hit on a great solution for. But the idea was that when given a word, it's actually going to process that word in smaller chunks. Specifically, I used 3-letter chunks. So it would go through a word, and for every 3 letters, it would try to sort of recognize that 3-letter chunk as sort of valid or not valid spelling. Again, this is pretty crude, and there's a lot more complexity to language, especially English spelling, than that. But ultimately, to do this, I needed to convert those words and those letters into numbers, into some sort of coordinate space that the self-organizing map could use to determine what closest node means. So I used a different kind of neural network, a more traditional one you may have seen in other videos, where I would feed in the three-letter word or three-letter subword chunks, and I would use that in the network to try and turn letters into numbers based on the letters that came before and afterwards. I'm not going to get too deeply into this. It turned out not to be a great way to do it, but it worked sufficiently well ultimately. I mean, neural networks, even when they don't seem like they're doing the right thing, they can get surprisingly close to good answers. So while I really wasn't happy with how that letter breakdown math worked, ultimately I let the neural net math do its thing. It took the letters, it sorted them, it gave them each number values, and that would have let me turn these three-letter subwords into coordinates, into numbers. So the feature map, the self-organizing map, would use those three-letter coordinates in the same way that I was using cones and spheres in that demonstration. It would try to find the best match node. It would tug the node and its neighbors in that direction. And ultimately, the result is not something that I could visually observe. So instead, the idea was that if it got in the three-letter subword and it didn't find a close enough match or didn't like it, it would substitute in something that it thought was better. And so it would take in three-letter subword chunks, it would spit out three-letter subword chunks, reassemble them, and then spit out a final word constructed from those chunks. So it would always have the same length of word as the input, so it didn't work if a letter was dropped off the end or added as the error, but it could fix a substitution letter. So for a letter in the middle of a word, that individual letter might be part of three subword chunks. So if the word is apple, that second P would first show up at the start of the word, so APP, it would be the end. And then PPL, it would be in the middle, and PLE, it would be at the front. And so other than the start and end of the word, each letter would appear in three of those subword chunks in different positions. And that means it's sort of getting three guesses as to what the correct letter should be. And when it's reassembling what it thinks is the correct spelling at the end, it would go with a majority rule. So out of those three attempts, if two of those or all three agreed, it would use that letter as the substitution. And if it had three different letters for the three different subword chunks, it would always pick the one represented by the middle chunk. So the PPL, if it had that guess, it would pick the P in the middle. Hard to explain. So this was an interesting and challenging use of neural nets, especially in those early days where we were still trying to figure out what might be done with them. Trying to translate letters into math was one of the bigger struggles of this project. Ultimately, the neural networks kind of worked out. I'll go over the results in a little bit. But definitely there were a lot of struggles around that process of trying to translate letters from words into numbers that a network could process in some mathematical way. And also other struggles, well, at the time, processor speeds being what they were, I was trying to keep these networks as small as possible. So while these days, hundreds of nodes with thousands of connections are pretty standard, possibly low end, at the time I was trying to do a 100 by 100 feature map. So 10,000 nodes, that's a lot for that time. And like I said, they would run overnight training several thousand iterations each night, and I could sort of save off the results and see if it was converging in a way that I liked, and I would either start over or let it process more time. So when I actually did this research long ago, I ran a few different tests, but I'll just talk about the one that I did at the end. This used a feature map of 10,000 nodes, 100 by 100, and a dictionary that sort of handpicked words to make sure I covered samples of letters properly. The dictionary was 1,363 words. It used a progressive training on the dictionary. And by that, what I mean is I would feed it a small number of words, train just those words for a little while, and when it had a good accuracy on them, I would add more words over time. So essentially, it grew into the dictionary over time while trying to maintain its accuracy. And ultimately, that worked out really well in the sense that as I would track its dictionary size and its success over time on new words that had been introduced, it would take it very little time to get to where it could recognize them and spell them correctly in this process where I feed it a word and it gives me as output what it thinks the word should be spelled like. So with this really large feature map, after about 500,000 iterations, which is, it was high at the time, but low in general for neural net training, it was up to 97% correct, where if it got a correct word in, it would give a correct word out. And of the words that it spelled incorrectly, all of them, all the other 3%, were only off by one letter. So that was a pretty good rate on familiar words. So while this network was excellent at recognizing its input dictionary and also reasonably good at learning new words that were fed to it, it really was not very good at correcting misspellings. So I'm not going to go into too many examples, but it was learning, it was converging, it was not really generalizing in the way that I'd hoped. So while I didn't achieve my goal of getting a neural network to generalize the rules and recognize new and made up words immediately, I did achieve a neural network that seemed to be capable of learning words relatively quickly and recognizing its training set, which ultimately is what these networks were known to be good for. They just did not generalize in the way that I wanted. And there's many reasons for that. And certainly the first and likely biggest reason is individual letters do not translate into math very easily. So I'm not going to get into all of those problems and details too quickly. But obviously, over time, people have overcome those hurdles. Computers have gotten more powerful. They can process bigger nodes faster. We have access to so much more data in convenient ways. I no longer would need to do a hand-typed dictionary if I were to continue this research, because we have many words already online for grabbing as samples. So hopefully this has given you an idea of how neural networks work. The ones in use today are way more sophisticated. I don't even really follow all of how they do what they do now. So this is more like an origin story, let's say, though. I don't think my work had any contribution to these final results. Anyway, I hope you enjoyed seeing how neural nets work and thinking about maybe how those simple ideas have have now led us into this much more complicated era where computers can write your homework papers for you or whatever. Write your own homework. So that's how neural networks kind of work. And this being a channel about game design, I gave some thought to, is there a way to use these kinds of networks, specifically the self-organizing feature maps, in a game? So I wouldn't recommend this for any sort of simple board game or tabletop game because it's way too mathy and requires thousands or millions of iterations. But in video games, there might be interesting ways to apply some of this. One of the ideas that I've had for this sort of thing is the idea that a video game could learn how to play based on how other players play. So let's just say, for example, you had an MMO and the developers wanted to make an automated NPC that could play like other players. One way to do that would be to gather the play information, where they go and when they activate their powers and in what orders, as inputs to some sort of self-organizing network. And so it would learn to play based on how people actually play. And then it could sort of imitate these styles, and especially the patterns that it sees the most often, which presumably would be some of the more successful ones. Could make it a decent player without being perfect, so it wouldn't necessarily feel like a hard-coded AI that's has its every action dictated by some math graph. But it would still be effective, and most interestingly, it would adapt and change as playstyles changed. So in games where either the players discover different ways to use the abilities or where the abilities change over time and require to be played differently, a neural net driven NPC could actually adapt to these changes through its continuous training and take on new behaviors that tend to match whatever trends of the players. I won't say instantly, it will take time to train it, but it will be playing like the player set of some weeks ago, let's say. Anyway, there's not a ton of applications for that, but if someone were to make a very immersive feeling game world where the NPCs actually interacted with the world in the way that the players do, that's one way to do it. And it wouldn't require somebody to program in and predict all of the things players might do. Instead, the game would literally mirror what players actually do. So there's a way to use neural networks in games. So in addition to talking about game design, this channel, these videos are a game. In each episode, you can earn a score. This has been built up, discussed over many other episodes. I'd recommend watching episode 0 if you're unfamiliar with how the scoring works. But there's a contest. In episode 10, I'm going to be giving away one copy of the Storyboard RPG. Hard to see up there, but as discussed in a prior episode. And that is going to the person who's got the highest score so far as of the time that I post episode 10. Who knows when that's going to be? This is episode 9. To simplify things for just this episode, episode 9, I'm just going to provide a prompt. And the prompt is, leave in the comments your best guess estimate as to the number of times I said the word network in this episode. And you'll score points equal to your guess as long as you don't go higher than the actual number of times I said that word. So that's an easy way to get some points. You can guess way low if you just want to get a number in. Or you can take a chance on a higher numbered guess to get more points. Next time on Game Design Game. Don't know. But episode 10, when I post it, that's when I will determine the contest winner. And I will get in touch with you through private message to send you your prize. Don't know what topic I'm going to cover yet. Haven't decided. So it's going to be a mystery. I hope you enjoyed this episode. Until next time, gamers, oh frabjous day, Kalu Kalay.